In the vast expanse of our cosmic backyard, beyond the familiar worlds we've come to know, lies one of the most bizarre objects ever discovered in our solar system. Picture a celestial body so peculiar it seems to have escaped from the pages of science fiction. Welcome to Haumea, the dwarf planet that defies our conventional understanding of planetary bodies. Unlike the spherical worlds we're accustomed to, this cosmic oddity takes the shape of a massive cosmic egg, spinning through the darkness of space at an astounding rate. While Earth takes 24 hours to complete a single rotation, Haumea accomplishes this feat in a mere 4 hours, making it one of the fastest spinning objects of its size in our entire solar system. This rapid rotation has literally pulled the dwarf planet into an elongated shape, stretching it like cosmic clay on a potter's wheel. As we venture deeper into the outer reaches of our solar system, Haumea stands as a testament to the incredible diversity of celestial objects that await our discovery. This remarkable world, named after the Hawaiian goddess of fertility and childbirth, continues to challenge our understanding of planetary formation and the fundamental physics that govern our cosmic neighborhood. Today, we embark on a journey to explore this enigmatic member of our solar system family, a world that reminds us that reality can sometimes be stranger than fiction. Haumea isn't just another space rock. It's a cosmic revolutionary, rewriting the rules of what we thought we knew about planetary bodies. Today, we venture into the far reaches of our solar system to explore one of its most enigmatic residents, Haumea. This fascinating celestial body, lurking in the distant Kuiper Belt approximately 43 times farther from the Sun than Earth, represents one of the most peculiar objects ever discovered in our cosmic neighborhood. What makes this distant world particularly remarkable isn't just its location, but rather its extraordinary characteristics that have left astronomers scratching their heads since its discovery. As we delve into the mysteries of Haumea, we'll uncover why this seemingly small world has created such excitement within the scientific community. From its bizarrely elongated shape that defies our traditional understanding of planetary bodies, to its astonishingly rapid rotation that warps its very structure, Haumea stands as a testament to the incredible diversity of objects in our solar system. This dwarf planet, named after the Hawaiian goddess of fertility and childbirth, has become a focal point of modern astronomical research, challenging our preconceptions about planetary formation and evolution. Its unique features, including crystalline ice surface, multiple moons, and newly discovered ring system, have transformed it from a mere distant dot in our telescopes into one of the most intriguing subjects in contemporary planetary science. As we embark on this cosmic journey together, prepare to discover why this small but mighty world continues to captivate astronomers and planetary scientists worldwide, and how its study is reshaping our understanding of the dynamic processes that govern our solar system's outer regions. The story of Haumea's discovery and classification represents one of the most intriguing chapters in modern astronomical history. The narrative begins in December 2004, when a team of astronomers led by Dr. Mike Brown at the California Institute of Technology first identified this peculiar object. Using the Palomar Observatory's Samuel Oskin telescope, they spotted what initially appeared to be just another distant trans-Neptunian object. However, subsequent observations revealed its extraordinary nature. The discovery process itself became the subject of controversy when a Spanish team of astronomers, led by José Luis Ortiz Moreno at the Sierra Nevada Observatory, published their own observations of the same object. This led to a complex debate about discovery credit and astronomical ethics that resonated throughout the scientific community. The years following its discovery were marked by intensive observation and analysis. Astronomers worked diligently to understand this object's unique characteristics, particularly its unusually rapid rotation and elongated shape. These studies culminated in a significant milestone in 2008 when the International Astronomical Union officially classified Haumea as a dwarf planet, making it the fifth officially recognized dwarf planet in our solar system, joining the ranks of Pluto, Ceres, Eris, and Makemake. This classification came during a period of major restructuring in our understanding of the solar system's architecture, following the controversial 2006 decision to redefine what constitutes a planet. Perhaps one of the most remarkable chapters in Haumea's story came in January 2017, when astronomers made an unprecedented discovery. During a stellar occultation event, where Haumea passed in front of a distant star, researchers identified a ring system encircling the dwarf planet. This discovery, published in the journal Nature, marked the first time a ring had been detected around a dwarf planet, adding another layer of complexity to this already fascinating object. The ring, approximately 70 kilometers wide and located about 2,287 kilometers from Haumea's center, rotates in the same plane as the dwarf planet's equator, challenging our understanding of ring system formation in the outer solar system. Each of these historical milestones has contributed to our evolving understanding of Haumea and the outer solar system. From its contested discovery to its official classification and the surprising revelation of its ring system, Haumea continues to write new chapters in astronomical history, demonstrating that even in an age of advanced space exploration, our solar system still holds remarkable secrets waiting to be unveiled. This chronological progression of discoveries has not only enhanced our knowledge of this particular celestial body, but has also prompted us to reconsider our broader understanding of planetary formation, dynamics, and the diverse array of objects that populate the outer reaches of our solar system. The ongoing study of Haumea serves as a reminder that astronomical discovery is a continuous process, often yielding unexpected findings that challenge our existing theories and push the boundaries of our scientific understanding. Among all known dwarf planets in our solar system, Haumea stands out as a true cosmic oddity due to its remarkable shape. Unlike the roughly spherical form we typically associate with planetary bodies, Haumea presents itself as a distinctly elongated ellipsoid, challenging our traditional understanding of celestial objects of its size. This extraordinary celestial body stretches approximately 2,100 kilometers at its longest axis, while measuring 1,680 kilometers across its intermediate axis and 1,074 kilometers along its shortest axis. To put these dimensions in perspective, if we were to scale Earth down to the size of a baseball, Haumea would resemble a stretched egg roughly half that size. This unusual geometry has earned Haumea colorful descriptions in astronomical literature, with scientists often comparing it to a cosmic rugby ball or an elongated egg tumbling through space. The physics behind Haumea's distinctive shape is fascinating and directly linked to its extreme rotational dynamics. As this dwarf planet spins on its axis at an incredibly rapid rate, the resulting centrifugal forces literally pull it into this elongated form. This process is similar to what happens when a pizza maker throws and spins dough in the air, though on a vastly different scale and time frame. The intense rotational forces have gradually stretched Haumea into its current form over millions of years. This unusual shape has significant implications for conditions on Haumea's surface. The gravitational field varies considerably depending on location, meaning that an object's weight would change depending on whether it was near the poles or the equator. The elongated shape also creates interesting variations in day length and solar exposure across different regions of the dwarf planet. The composition of Haumea plays a crucial role in maintaining this unusual shape. Studies suggest that it consists primarily of rock with a thin outer layer of crystalline ice. This composition provides enough structural integrity to maintain its elongated form, while still being malleable enough to be affected by rotational forces. The presence of crystalline ice, rather than amorphous ice, indicates that Haumea has experienced significant heating events in its past, possibly related to the same processes that gave it its rapid rotation. Understanding Haumea's shape has been crucial in developing new theories about the formation and evolution of dwarf planets and other large bodies in the outer solar system. Its unique form suggests a violent past, possibly involving a massive collision that not only shaped its current appearance, but also led to the formation of its moons and ring system. This makes Haumea an invaluable natural laboratory for studying the complex dynamics of planetary formation and evolution in the outer solar system. Recent observations continue to refine our understanding of Haumea's shape, with each new study providing more precise measurements and insights into the forces that created and maintain this remarkable configuration. The dwarf planet's unusual form remains one of the most compelling examples of how diverse and unexpected planetary bodies can be, challenging us to expand our understanding of what's possible in our cosmic neighborhood. One of the most extraordinary features of Haumea is its remarkable rotational speed, which sets it apart as the fastest spinning large object known in our solar system. This cosmic ballerina completes one full rotation in just 3.9 Earth hours, a velocity so extreme it fundamentally affects the dwarf planet's physical structure and behavior. To truly appreciate the magnitude of this rotation, Consider that while Earth leisurely completes one rotation every 24 hours, Haumea spins more than 6 times in that same period. This breakneck rotational speed generates immense centrifugal forces that literally reshape the dwarf planet. The physics at play here is similar to what happens when you spin a ball of soft clay, except on an astronomical scale. The centrifugal force, which pulls outward from the center of rotation, works against the dwarf planet's gravity, which pulls inward. This opposing force relationship has stretched Haumea into its characteristic elongated shape, much like a water balloon being spun rapidly. The speed of rotation is so significant that if Haumea were to spin just a little faster, it would literally tear itself apart. Scientists believe it's rotating at nearly the critical speed, the theoretical maximum rotation rate that a body can sustain before breaking up due to centrifugal forces. This places Haumea in a fascinating physical state where it's maintaining a delicate balance between gravitational cohesion and rotational disruption. To put this extreme rotation in perspective, an object on Haumea's equator would experience a significantly reduced effective gravity compared to one at its poles, due to the counteracting centrifugal force. This variation in effective gravity across the surface creates unique geological conditions that we don't observe on any other known dwarf planet. The origin of this rapid rotation remains one of the most intriguing mysteries surrounding Haumea. The leading theory suggests that a massive collision in the distant past set the dwarf planet spinning at this extraordinary rate. This same impact event might have also been responsible for creating Haumea's moons and contributing to the formation of its ring system. The collision would have needed to be precisely angled and energetic enough to impart this specific rotational momentum without destroying the object completely. Understanding Haumea's rotation has profound implications for our knowledge of planetary formation and evolution. Its extreme spin rate provides valuable insights into the physical limits of rotating celestial bodies and helps us understand how impacts and collisions shaped our solar system's history. The dwarf planet serves as a natural laboratory for studying the effects of extreme rotation on planetary bodies, challenging our models of planetary physics, and forcing us to expand our understanding of what's possible in terms of planetary dynamics. Recent observations continue to refine our measurements of Haumea's rotation rate and its effects, with each new study providing additional insights into this remarkable celestial dance. The combination of its rapid rotation and unusual shape makes Haumea one of the most fascinating objects in our solar system, demonstrating that even after centuries of astronomical observation, the cosmos still holds surprises that challenge our understanding of fundamental planetary physics. Orbiting in the distant reaches of our solar system, Haumea's peculiarities extend beyond its rapid rotation and unusual shape to include a fascinating family of satellites. This remarkable dwarf planet hosts 2 known moons, each with its own intriguing characteristics and mysterious origins. These natural satellites, named Hiʻiaka and Namaka after Hawaiian mythological figures, add another layer of complexity to this already extraordinary celestial system. Hiʻiaka, the larger of the 2 moons, measures approximately 310 kilometers in diameter and orbits Haumea in a nearly circular path every 49 Earth days. Named after the Hawaiian goddess of hula dancers and patroness of the Big Island of Hawaii, Hiʻiaka reflects enough light to suggest it's covered in pure water ice crystals, much like its parent body. Its substantial size makes it a significant player in the Haumea system, with enough mass to exert notable gravitational influences on its smaller sibling and the dwarf planet itself. The smaller moon Namaka, named after a water spirit in Hawaiian mythology, is roughly 170 kilometers across and completes its orbit around Haumea every 18 Earth days. Despite its smaller size, Namaka plays a crucial role in the dynamic dance of this celestial family. Its orbit is notably more elliptical than Hiʻiaka's, suggesting a complex gravitational relationship between all 3 bodies. What makes this system particularly fascinating is the likely story of its formation. Astronomers believe that Haumea's moons weren't captured objects, as is the case with some other planetary satellites. Instead, they're thought to be fragments from a massive collision that occurred billions of years ago. This same violent event is believed to have set Haumea spinning at its current remarkable rate and may have been responsible for ejecting numerous other ice-rich fragments into similar orbits around the Sun, creating what we now call the Haumea family of objects. The orbits of both moons are nearly coplanar with Haumea's equator, providing strong evidence for their collisional origin. This alignment is unlikely to have occurred if the moons were captured objects, supporting the theory that they formed from debris ejected during an ancient impact. Their orbits also exhibit a fascinating resonance pattern, with Hiʻiaka completing exactly 3 orbits for every 8 of Namaka's, creating a complex gravitational dance that has helped maintain the stability of this remarkable system over billions of years. The presence of these moons has proven invaluable to astronomers studying Haumea. By carefully observing their orbital motions, scientists have been able to calculate Haumea's mass and density with remarkable precision. These measurements have revealed that Haumea is surprisingly dense for an object in the Kuiper Belt, suggesting it's composed primarily of rock rather than ice, despite its bright, ice-covered surface. Recent observations have also revealed that both moons, like their parent body, are covered in crystalline water ice, a form that requires specific temperature and pressure conditions to form. This shared characteristic provides additional evidence for their common origin and offers clues about the conditions present during and after the collision that created this remarkable family of objects. The study of Haumea's moons continues to yield new insights into the processes that shaped our solar system. Their existence and properties help us understand the complex dynamics of collisions in the outer solar system, the formation of multiple body systems, and the long-term evolution of dwarf planet satellites. As our observational capabilities improve, these distant companions may yet reveal more secrets about their mysterious parent world and the fascinating dynamics of the outer solar system. So, deep space explorers, are you enjoying this trip to Haumea? If so, don't forget to like the video and subscribe to the Exploring the Universe channel. And tell me in the comments, if you could name a geological feature in Haumea, what would you name it and why? Your creativity can be as unique as this dwarf planet. The study of Haumea extends far beyond mere astronomical curiosity, offering profound insights into fundamental cosmic processes and enriching our understanding of the solar system's complex dynamics. This remarkable dwarf planet serves as a natural laboratory, providing valuable lessons across multiple scientific domains and challenging our existing models of planetary formation and evolution. In terms of outer solar system formation and evolution, Haumea acts as a cosmic time capsule, preserving evidence of our solar system's turbulent past. Its unique characteristics, from its elongated shape to its family of associated objects, provide crucial clues about the conditions and processes that shape the outer reaches of our cosmic neighborhood. The dwarf planet's composition and structure suggest a dynamic history of impacts and interactions, helping astronomers reconstruct the solar system's violent early years. This understanding is vital for developing more accurate models of planetary system formation, which has direct applications in studying exoplanetary systems around other stars. The physics of rapidly rotating bodies finds a remarkable exemplar in Haumea. Its extraordinary spin rate and resultant shape offer an unprecedented opportunity to study the behavior of large celestial bodies under extreme rotational conditions. This natural experiment helps validate theoretical models of fluid dynamics and material physics at astronomical scales. The insights gained from studying Haumea's rotation have practical applications in understanding the stability limits of rotating bodies, which is crucial for designing artificial satellites and predicting the behavior of other astronomical objects. Haumea's presence in the Kuiper Belt highlights the remarkable diversity of objects in this distant region. As one of the largest and most unusual Kuiper Belt objects, it demonstrates that this region is not merely a collection of identical icy bodies, but rather a complex ecosystem of varied celestial objects. This diversity challenges our previous assumptions about the outer solar system and forces us to expand our understanding of planetary formation processes. The study of Haumea and its fellow KBOs helps us develop more comprehensive models of planetary system architecture and evolution. The processes of collision and moon formation revealed by the Haumea system provide crucial insights into the mechanics of planetary impacts and their aftermath. The presence of its moons, ring system, and associated family of objects in similar orbits tells a story of cosmic collisions and their long-term consequences. This knowledge is invaluable for understanding similar processes throughout the solar system and beyond. The study of these collision processes helps us better understand planetary protection strategies and the potential consequences of cosmic impacts. Beyond these primary areas, Haumea's study has catalyzed advances in observational techniques and technology. The challenges of studying such a distant and complex object have driven innovations in astronomical observation methods and data analysis. These technological and methodological advances have applications beyond astronomy, influencing fields such as imaging technology, data processing, and remote sensing. The dwarf planet's unique characteristics have also contributed to our understanding of ice physics under extreme conditions. The presence of crystalline water ice on its surface, despite the incredibly cold temperatures of the outer solar system, provides insights into the behavior of materials under various temperature and pressure conditions. This knowledge has applications in materials science and our understanding of geological processes on icy worlds. From a broader scientific perspective, Haumea serves as a reminder of the importance of challenging established paradigms. Its discovery and subsequent study have repeatedly shown that the solar system is more complex and diverse than previously imagined. This lesson in scientific humility and the importance of remaining open to unexpected discoveries has implications across all scientific disciplines. These scientific implications continue to evolve as new observations and studies reveal more about this fascinating world. Each new discovery about Haumea not only enhances our understanding of this specific object, but also contributes to our broader knowledge of planetary science, physics, and the fundamental processes that shape our cosmic environment. As our observational capabilities improve and new theoretical models are developed, Haumea's study will undoubtedly continue to yield valuable insights and practical applications across multiple scientific domains. Dr. Mike Brown's perspective on Haumea opens a fascinating window into the scientific community's evolving understanding of our solar system. As one of the leading planetary astronomers and the discoverer of numerous trans-Neptunian objects, including Haumea, his insights carry particular weight in the field of planetary science. His characterization of Haumea as the rebel of the solar system perfectly encapsulates the dwarf planet's role in challenging our established understanding of celestial bodies. The scientific implications of Haumea's rebellious nature run deep. When astronomers first began discovering large objects in the outer solar system, they generally expected to find roughly spherical bodies, similar to the classical planets and other known dwarf planets like Pluto. Haumea shattered these expectations. Its elongated shape, extraordinary rotation rate, and complex system of moons and rings represent a departure from conventional models of planetary formation and evolution. Other prominent astronomers have built upon Dr. Brown's observations. Dr. Pedro Lacerda from the Queen's University Belfast has noted that Haumea's rapid rotation and high density suggest a violent collision early in its history, possibly stripping away much of its ice mantle. This hypothesis helps explain both its unusual shape and the creation of its associated family of objects, including its moons. Dr. José Luis Ortiz, whose team made the groundbreaking discovery of Haumea's ring system in 2017, emphasizes how this finding further compounds the dwarf planet's peculiarity. As he explains, the presence of a ring system around such a small, rapidly rotating body defies our previous assumptions about where and how planetary rings can exist. The astronomical community has been particularly intrigued by what Dr. Amanda Sikafous of the South African Astronomical Observatory calls the Haumea paradigm. The idea that our solar system harbors far more diversity in planetary bodies than we previously imagined. This concept has encouraged astronomers to look beyond traditional parameters when studying other distant objects. Dr. David Jewett, a pioneer in Kuiper Belt research, points out that Haumea's unique characteristics have forced a reassessment of planetary formation models. The dwarf planet's high density and rocky composition, combined with its crystalline water ice surface, suggest a complex formation history that doesn't neatly fit into existing theories. According to Dr. Sarah Ballard of MIT, Haumea serves as a crucial reminder that our solar system's formation was likely far more chaotic and dynamic than previously thought. The dwarf planet's unusual properties provide evidence for significant collisions and interactions between large bodies in the early solar system, supporting models of planetary migration and dynamical instability. Dr. Michelle Bannister from the University of Canterbury emphasizes how Haumea's study has influenced our approach to observational astronomy. Its discovery and subsequent characterization have led to improved techniques for detecting and studying distant solar system objects, particularly those with unusual shapes or rapid rotations. The scientific community continues to debate various aspects of Haumea's nature and origin. Dr. Wesley Fraser of Queen's University Belfast suggests that understanding Haumea's formation might provide crucial insights into the early solar system's dynamics. His research indicates that the collision that shaped Haumea might have occurred during a period of significant planetary migration, potentially linking the dwarf planet's unusual properties to broader solar system evolution. These expert perspectives collectively emphasize how Haumea has become a crucial case study in planetary science. As Dr. Brown noted, it continues to challenge our expectations and force us to reconsider our models of planetary formation and evolution. The dwarf planet serves as a reminder that even after centuries of astronomical observation, our solar system can still surprise us with objects that defy conventional understanding. The ongoing study of Haumea, supported by advancing observational technologies and refined theoretical models, promises to reveal more surprises. As we continue to probe this fascinating world, each new discovery adds another piece to the puzzle of our solar system's formation and evolution, while potentially raising new questions that challenge our understanding of planetary science. Haumea continues to amaze astronomers with its collection of remarkable features and characteristics. Let's explore some of the most fascinating facts about this distant world that make it truly unique in our cosmic neighborhood. One of the most intriguing aspects of Haumea is how your weight would change depending on where you stand on its surface. Due to its elongated shape and rapid rotation, the gravitational pull varies significantly across different locations. If you could somehow stand on Haumea's equator, you would weigh considerably less than at its poles, as the centrifugal force partially counteracts gravity. This variation in gravitational pull is far more extreme than anything we experience on Earth or other known planetary bodies. The dwarf planet's surface is remarkably reflective, with an albedo, reflectivity measure, comparable to fresh snow. This high reflectivity comes from a coating of pure crystalline water ice, making Haumea one of the brightest objects in the Kuiper Belt. The presence of crystalline ice is particularly puzzling because, at the frigid temperatures of the outer solar system, water ice typically exists in an amorphous, non-crystalline state. This suggests that some form of geological activity or past event has processed the ice into its crystalline form. In a surprising astronomical event in 2017, scientists discovered that Haumea possesses a ring system, making it the first known dwarf planet with rings. This discovery occurred during a stellar occultation, when Haumea passed in front of a distant star. The ring is approximately 70 kilometers wide and orbits in the same plane as Haumea's equator, at a distance of about 2,287 kilometers from the dwarf planet's center. The temperature variations on Haumea are extreme even by outer solar system standards. Surface temperatures can range from about minus 241 degrees Celsius to minus 225 degrees Celsius, depending on the location and exposure to sunlight. Despite these frigid conditions, the dwarf planet's surface shows signs of geological processing that scientists are still working to understand. A fascinating aspect of Haumea's composition is that it appears to be almost entirely composed of rock, with only a thin outer layer of ice. This makes it unusually dense for a Kuiper Belt object, with a density similar to Earth's moon. This composition suggests a violent past event that may have stripped away much of its original ice mantle. The dwarf planet's rapid rotation creates a day that lasts just under 4 hours, making it one of the fastest rotating large bodies in our solar system. This speed is so extreme that if Haumea were to spin just a little faster, it would literally begin to break apart. The rapid rotation also creates interesting phenomena like variable sunlight exposure patterns across its surface that are unlike anything seen on other planetary bodies. Another remarkable feature is Haumea's family of objects. Besides its 2 known moons, Hiʻiaka and Namaka, there are at least 10 other known objects in the Kuiper Belt that appear to have originated from Haumea. These objects share similar orbital characteristics and surface compositions, suggesting they were all once part of a larger body that was involved in a massive collision. The naming of Haumea and its moons connects deeply with Hawaiian mythology. Haumea was the goddess of fertility and childbirth, while Hiʻiaka was her favorite daughter and Namaka was a water spirit. This naming convention reflects the astronomical community's effort to connect celestial objects with various cultural mythologies and traditions. Perhaps one of the most surprising facts is that despite its significance and unique characteristics, we have never seen Haumea up close through spacecraft observations. Our understanding of this remarkable world comes entirely from Earth-based telescopes and careful astronomical calculations, making its list of unusual features even more impressive considering the vast distance from which we study it. These fascinating aspects of Haumea continue to challenge our understanding of planetary science and demonstrate that our solar system is far more diverse and complex than we once imagined. Each new discovery about this distant world adds another piece to the puzzle of our cosmic neighborhood's history and evolution. The study of Haumea presents a fascinating array of scientific challenges, while simultaneously opening new frontiers for future exploration. As we continue to probe this distant world, we face significant obstacles in our quest for understanding, but emerging technologies and planned missions offer promising opportunities for breakthrough discoveries. One of the most pressing current challenges lies in understanding Haumea's internal structure. While we can observe its external characteristics, the dwarf planet's interior remains largely mysterious. Scientists struggle to reconcile its high density with its rapid rotation and elongated shape. Current models suggest a primarily rocky composition with a thin ice shell, but confirming these theories requires more precise data about its mass distribution and internal layering. The interaction between its internal structure and its extreme rotation rate presents a complex puzzle that challenges our current geological and physical models. The origin of Haumea's remarkable rotation rate continues to puzzle astronomers. While the leading theory suggests a massive ancient collision, the exact mechanisms that could have produced such rapid spin while maintaining the object's structural integrity remain debatable. Understanding this aspect requires advanced computer modeling and additional observational data to test various formation scenarios. The challenge lies not only in explaining the initial impact, but also in understanding how the rotation rate has evolved over billions of years. Studying Haumea's ring system and moons presents another significant challenge. The extreme distance and small size of these features make detailed observations difficult with current technology. Questions remain about the ring's composition, age, and formation mechanism. The dynamic interactions between Haumea, its rings, and its moons form a complex system that requires sophisticated orbital mechanics to fully understand. Current telescopes struggle to provide the resolution needed for detailed analysis of these features. Looking toward the future, several promising developments may help address these challenges. The upcoming generation of ground-based telescopes, including the extremely large telescope and the 30-meter telescope, will provide unprecedented observational capabilities. These instruments will offer higher resolution images and more detailed spectroscopic data, potentially revealing new features on Haumea's surface and providing better observations of its moons and ring system. Space-based telescopes will also play a crucial role in future observations. The James Webb Space Telescope's infrared capabilities could provide new insights into Haumea's surface composition and temperature variations. Future space telescopes may offer even more detailed views of this distant world and its surroundings. Perhaps the most exciting future prospect involves potential dedicated missions to the outer solar system. While no missions are currently planned specifically for Haumea, the success of New Horizons' Pluto flyby has demonstrated the value of close-up observations of distant worlds. Technical challenges remain significant. The extreme distance requires advanced propulsion systems and long travel times, while the dwarf planet's rapid rotation poses unique challenges for imaging and data collection. Emerging technologies in spacecraft design and propulsion systems may eventually enable missions to reach Haumea more quickly. Advanced ion engines, solar sails, or nuclear propulsion systems could potentially reduce travel times to the outer solar system. Such missions would revolutionize our understanding of Haumea and similar objects in the Kuiper Belt. Improvements in computer modeling and simulation capabilities will also play a crucial role in future studies. Advanced simulations could help us better understand Haumea's formation, internal dynamics, and the complex gravitational interactions within its system. Machine learning algorithms might help process the vast amounts of observational data more effectively, potentially revealing patterns and features that human analysts might miss. The development of new observation techniques, such as improved stellar occultation methods, could provide more detailed information about Haumea's size, shape, and ring system. These techniques, combined with better coordination between observatories worldwide, could yield more precise measurements of Haumea's physical characteristics. International collaboration will be crucial in advancing our understanding of Haumea. The complexity and cost of studying such a distant object require coordinated efforts between multiple space agencies, observatories, and research institutions. Future discoveries will likely emerge from combined efforts using multiple observation platforms and analytical techniques. As we look to the future, the study of Haumea promises to continue challenging and expanding our understanding of the solar system. Each new technological advance brings us closer to answering fundamental questions about this fascinating world, while inevitably raising new ones. The coming decades may reveal aspects of Haumea that we can barely imagine today, making it an exciting frontier in planetary science for generations to come. As we conclude our journey through the fascinating world of Haumea, we find ourselves in awe of this remarkable celestial object that continues to challenge our understanding of the solar system. This distant dwarf planet stands as a testament to the incredible diversity that exists in our cosmic neighborhood, proving that reality can often surpass our wildest astronomical imaginations. Throughout our exploration, we've witnessed how Haumea defies conventional planetary characteristics at every turn. Its egg-like shape, unprecedented among known dwarf planets, results from one of the fastest rotation rates observed in our solar system. This rapid spin, completing one revolution in just under 4 hours, has literally pulled the dwarf planet into its elongated form, creating a world that seems to dance through space like no other. The presence of its 2 moons, Hiʻiaka and Namaka, adds another layer of complexity to this already intriguing system. These satellites, likely born from the same violent collision that gave Haumea its rapid rotation, orbit their parent in an intricate gravitational dance. The discovery of Haumea's ring system in 2017 further cemented its status as one of the most surprising objects in our solar system, making it the first known dwarf planet to possess such a feature. The scientific implications of Haumea's unique characteristics extend far beyond its individual study. Its properties have forced us to reconsider our models of planetary formation and evolution, suggesting that the early solar system was a far more dynamic and chaotic place than previously thought. The presence of crystalline ice on its surface, despite the extreme cold of the outer solar system, hints at complex geological processes we are only beginning to understand. Perhaps most importantly, Haumea serves as a humbling reminder that our solar system still holds many secrets waiting to be discovered. After centuries of astronomical observations and technological advances, we continue to find objects that challenge our preconceptions and expand our understanding of what's possible in our cosmic backyard. Looking to the future, Haumea remains a prime target for continued scientific investigation. As our observational capabilities improve and new space missions venture into the outer solar system, we may uncover even more surprises about this remarkable world. Its study not only enriches our understanding of the solar system's diversity, but also reminds us of the boundless wonders that await our discovery in the cosmos. Haumea stands as a cosmic revolutionary, rewriting the rules of what we thought we knew about planetary bodies. In its distant orbit, it continues to intrigue astronomers and inspire new generations of planetary scientists, proving that in the vast theater of space, even relatively small objects can steal the show and lead us to profound new insights about our cosmic environment. This extraordinary dwarf planet, with all its peculiarities and mysteries, exemplifies why we continue to explore and study our solar system. Each new discovery about Haumea adds another piece to the grand puzzle of our cosmic neighborhood, while simultaneously presenting new questions that drive us to look deeper into the mysteries of space. As we continue to study this fascinating world, we can only imagine what other secrets it may yet reveal about the nature and history of our solar system.